Good evening, colleagues. So today we have very interesting talk by Antonina Dolgorukova. She will present a solution which was top 2 on the public leaderboard and in the gold zone on the private leaderboard. Was a very interesting biological bioinformatics challenge on the Kaggle to predict the binding of small molecules to the proteins. So Antonina and her team obtained a great solution, and thank you very much that you agreed to make a talk, and please start.
Hello, everyone, and thank you, Alexander, for inviting me and for this opportunity to share our solution, my voice to others. And yes, so I'll tell you a little bit about our solution for this NeurIPS 2024 competition. This was a great competition for for many reasons actually, and my third. It lasted almost 3 months, and from April to July, and we all had very hard work on it during all these 3 months, and we fight it to the very end and made our last submission for in the final day, 22 days from now. And yes, to the end of this competition, we were a few weeks at the first place and ended up at second place in the public leaderboard. But on the private leaderboard, we dropped down to 13th place, which is not too bad because we survived with gold medal. And actually, we were the only one team who stayed at the gold medal zone in both leaderboards. And maybe this is why the solution maybe is interesting to someone as a robust one. Yeah, and you also can see above us a lot of teams came here from the very, very low. And also interesting note here is that we did our last submit at the last day of the competition, but some prize contenders did their last submission like somewhere in the middle of this competition and just maybe gave up. I imagine they just were experimenting, selected so maybe good, maybe random submits, and woke up at the private leaderboard assessment day and find their self as prize contenders. Maybe not. Anyway, any of these 3 teams did not publish their solution, which is very bad for us as a community, but maybe they will after this. Anyway, would be interesting to see their approaches. What about ours? First of all, I need to tell a little bit about this competition in overall, so that you could understand what we did and why. So here our main objective was to solve a classification task and to build predictive models to estimate the probability of binding of chemical compounds to 3 proteins, 3 specific targets. And here is training data, and you can see the first column. We had 98 million molecules or chemical compounds represented as SMILE strings. And here is an example of conversion from SMILEs to molecular graph. So you can see just so you can just see that SMILEs are linear notations of molecular structure, just simple. And we had these SMILEs in the first column, and also we had in our training data information for each compound, whether it binds or not binds to each of the 3 proteins. But that's not all we had. You can see here 3 more columns. That is because each molecule in this competition consisted of a core and 3 different building blocks attached to it. So in these three columns, we have smiles for each of these three molecular parts. Also, it is important to note that from a relatively small number of different building blocks, just using different combination of them, we can get a very, very huge number of different molecules. So in this competition, almost 100 million of molecules were made from just around 2,000 of building blocks. Quite small number relative to number of molecules. And the bigger half of these building blocks is shared between train and test molecules, while the smaller part is present only in test molecules. So these are non-shared building blocks. This table, you can see more precise numbers by building block position, how many different building blocks was in train and test molecules, how many was at common, and for each building block position, how many new or non-shared building blocks had test molecules. That's important information, because all of this can lead us to a simple conclusion that our test had at least two different parts, right? In one, we have molecules which are quite similar to train, and in other part, we have molecules which are completely different from the train, because they all composed from different building blocks. And this is true, but actually in our test data set,
Antonina, I'm sorry.
we have not two, but
can you
three groups.
go
Yeah.
to the previous slide just to question?
Yeah. Okay.
So the first column, molecule, this is the column for both the core and building blocks, or only for the core? So on your picture,
this one.
Yes.
This is yeah. These are smiles for the chemical compounds we have to predict for molecules,
Okay.
our molecules.
So
and these are smiles for building blocks.
Okay, for this building blocks, so they are part of this first column or not?
Yeah, part, but not exact much, because it's it's a complicated process with different kind of reactions, where you can take different building blocks, and they undergo different reactions, and some parts like separated, and in the final molecule we have not the full structure. So these are not just substructures of the molecule. They are original little molecules from which this final molecule was made. Is it clear?
Okay. So it was made of these three blocks, but something might be lost during this building process. Okay, so it's not. But just another question.
Yes.
On your picture at the right corner, bottom right, I see the picture.
This one.
Yes. There are three in the circles. I thought it's kind of building block, and there is something in the middle which is not you. So it seems like you have something like a core block, which three building blocks are
like
or this is just misleading picture. So there is no core. So.
Like just I said. Like just I said, yeah. Each molecule in this competition consisted of a core and three building blocks attached to it. And
okay, but
also to one build, I can
information about this core. It's not in the columns. Yes.
Core. This is trisine core specific one. Yeah.
But is it in the columns or it's not in the columns? The
Columns?
yes. The central part, the central part.
It's in the first one,
No,
right?
we don't have we don't have separate column because it is the same core. All the train molecules had the same core, tyrosine core.
They have the same core.
So the same structure.
Okay.
Same that, yeah. That's yeah.
Okay.
And
all of them.
Yes, and may I ask small question? If then you have a SHA column with one flag, so it means it can bind to this protein, right? Like
this means like this first chemical can bind to this protein and do not bind to other two.
right. And why the
Zeros.
amount of building blocks is so small relative to training examples? Because like we only have
you can use yes you can use different reactions and combine these building blocks by different way. So different molecules in our training set are just different combinations of the same building blocks.
I see. Thank you. That's
it's
why
like
you have so many
combinations.
So that's why you have so many training examples out of so small building blocks. It's another way. Thank you.
Yeah.
Okay, I get it.
Thank you. Okay, thank you for the questions. Okay, so so in our test data, we had actually 3 distinct groups of molecules. 42% of test molecules are just like I described it now, composed of tyrosine core, all had the same core, and 3 distinct building blocks also present in train data, same as in train. We call this part shared building blocks, shared between test and train. And it was 42% of them. And there is also very, very little part of test data of 2.6% of molecules, which had the same tyrosine core, but different building blocks not present in train data. We call this part as non-shared molecules with non-shared building blocks. And the most of the biggest part of the test data set is composed of molecules with completely different 38 cores and different building blocks. This is so-called new library molecules. And this what made this competition so outstanding and difficult.
I'm sorry, can you repeat this? So what is
yeah.
this? So the cores are again the same tyrosine cores, yes? No?
For this part,
yes.
right?
Yes.
Yeah, this completely different molecules from the new library made from different cores, 38 different cores.
Not tyrosine, but something.
Not tyrosine.
Okay. But so they are not completely in the train. There was no
one present in train.
Okay. And building block for them were the same or also new?
Also new.
Okay, I see. Yeah, very sure.
Yeah.
Thank you.
So we're very different molecules, not only by cores, but also by building blocks. And if we split our test data further by private and public subsets, we can see that public subset of our test molecules have only 2 groups, don't have any of these new molecules, and mostly represented by molecules with shared building blocks, and a very, very small amount of molecules with non-shared to train building blocks. And in contrary, private part of the test set is formed by the molecules from this new library, 71% from new library. And almost equal distribution of shared and non-shared molecules with shared and non-shared building blocks as here, but mostly from new library molecules. So you already can guess why we did have so huge shakeup, right? The metric for this competition was mean average precision. And it also was calculated differently for public and private leaderboards. For public score, it was calculated across 6 different groups, because we also have 3 proteins. And for each protein, we have these 2 groups of molecules. So we have 6 average precision scores, and after we calculated 6 scores, we just take an average and and we got our mean average precision in the leaderboard. That is for public leaderboard. And for the private leaderboard, mean average precision was calculated across 9 groups, because here we also have new library molecules for each protein to predict for. Any more questions about how it was all, or is clear? Okay, I guess it's clear, because it's so challenging to make such a complicated split for public and private.
Did the organizers explain why they
Yes.
made so complicated? So it was shake-up proning.
Sorry.
Did the organizers explain why they choose such a split, which a kind of shake-up proning?
Promising. Shake-up was expected, obviously. Yeah.
So why did
I will highlight this little further, maybe next slide, because maybe I will talk about this. Why they did this? Because actually their main goal was to predict for this part, for new library. That is why the private leaderboard test consists mostly of these molecules. They wanted to get a model which generalizes well to this new chemical space with completely new molecules. No one achieved this.
Then still it's strange why they put only tyrosine cores in the training set. Why didn't they?
It does, but there are some complications with, you have to make a lot of experiments. It's experimental work to get all the data. Maybe they just didn't good representative samples with different cores. I don't know. That's
okay.
That
Thank you.
question we should ask from organizers, not for me. So about our solution for solving this task, we did not use any unusual model. All model we used, other participants did use too. So maybe in our solution, I guess, what make it apart from others is 2 little things, maybe not little. One of which is we used separate approaches for molecules with shared and non-shared building blocks. I guess it maybe seems obvious after these pictures. Maybe not for all. Actually, I saw some solutions who also did this different ensembling for these 2 parts of test, but I guess not all. And actually very few solutions were shared and published after the competition ended. Such a pity. Anyway, here I was trying to depict, to visualize why it is seems reasonable to use different approaches for these different parts tests of the test set. We can imagine our chemical space, entire chemical space, I mean, in test and train subsets, and different groups. I color it with different colors. And in blue are molecules made from the same building block set. For these molecules, we can assume that they all came from the same population of alike molecules from the same set. And if this assumption is right, we just can overfit as much as possible to the trained data and use for validation any subset, any random part of the train, and also for local scores, and come up with a good model for this part. And I can confirm that that is true because we had almost perfect correlation between scores, between local scores on our local test, just randomly subsetted from the train, with both public and private test, even if we tried different folds for validation. All the scores from local assessment correlated very, very well with public and private scores. And with random split, we just get a subset of molecules. All of them have the same building blocks as train. So all of this seems quite easy. But the next group I colored in orange and yellow colors, and these are molecules made from a distinct set of building blocks. I did use different colors here because building blocks in public and private test are also differ from each other. Yeah. So how do we predict binding to proteins for these molecules? There are at least two different options. First of all, we can simulate this situation where model is trained on molecules with one set of building blocks and makes predictions for molecules having different different building blocks. To do this, we just can just like separate a part of building blocks in train and select molecules having only these specific building blocks and use these molecules for validation and local testing, local scoring. In such a way, it looks like our train and test look like our train versus public test or versus private test, right? We did try this approach, and even we included one model trained exactly this way in our final solution, but only one. And we, because there was one problem with this approach. If we try different validation folds, we could get very, very different scores with them. And these scores did not correlate well with public leaderboard scores at all. With a huge degree. The variation between scores on different validation folds was very, very huge. Meaning that, how did we do this? We just withhold 20% of building blocks from train and separated only molecules with these building blocks, and we got a sample of 500,000 molecules for validation and another 500,000 molecules for test, local test. From the remaining molecules, we had to filter out all containing any of these validation building blocks at any position. So we had only 50 million molecules in the train. Seems enough. But already is a half of an entire train set. So with this validation fault or test fault of 500,000 molecules, we got very, very different scores depending on what building blocks we separated from the train. Meaning that even 500,000 is not enough to get a representative validation set, which would reflect model ability to generalize to new molecules with distinct building blocks. So what we can say about scores for this test part, public and private, if we remember the numbers, these parts are green, we are talking about, and they consist only of 11,000 of molecules. Can this be representative? I guess not. So I would say that leaderboard scores for this test part cannot reflect model's ability to generalize, but rather reflect model's ability to predict binding to proteins for this specific set of molecules. So in my opinion, these scores are not useful at all for solving the task the hosts wanted us to solve. Anyway, considering these small sample sizes and this variation in local scores, we concluded it is better to we concluded that it is highly likely that molecules in private test of this group will be more similar to molecules in public test more similar with public than with molecules from the train. So we just used public leaderboard scores for model selections in our ensembles. Any questions for now?
Yes.
Is it part maybe not clear because it's kind of difficult?
Can you please again say, so what is the difference between public, private, and this validation with non-shared BB? So public or private, it has different not tyrosine cores. This is main difference, or the main difference is that the building blocks are different.
No. Yeah, if you look at this again, we have 3 different groups.
Yes,
and here I just used different colors. I also plotted the same 3 groups, but in different way. And the first group in blue is like here, blue part, molecules with shared building blocks. And these orange and yellow molecules from test here are these parts, green. Molecules with the same tyrosine core, but different building blocks.
Okay.
And the third group, molecules from the new library, here are in green, and here are in red, this biggest part of the test. So I just wanted to say that...
So you say that you decided that we should look on the public test scores as a kind of better proxy for private test scores for this part. Yes, this is correct.
Yes.
And why it is like this? I didn't catch the idea.
The idea, at least 2 reasons. Because it would be more reliable to figure out how to make a good validation fault, right? Representative, which would reflect the ability of models to generalize to models with distinct building blocks. If we did so, we would have a validation fault on which we could get scores, and these scores would correlate with both public and private tests because it would be a representative validation fault, right? I just saying that it was not possible in this competition to make such a fold. Maybe it was, but we didn't figure out how to do this.
Yes, but then why you expected that public would better correspond than any of this? Why you expected public would better correspond to private? If there is no correlation between the your validation and public, maybe you can expect there will be neither not correlated public and private.
Yeah, all three of them could be, all three of these our like hypothetical validation part of the train and public test and private test, all three of them could be just different samples with some scores on it. Yeah, but we expected they would be similar because of several reasons. It would just be, it was just a guess, okay? Because it seems more logical to have like to divide one sample, like this one sample of green molecules with not shared BB to two, just randomly divide to private and public, right?
Okay.
So we just made a request that they did so. They just divided it. Actually, it happens that they did it another way because building blocks in private and public also differ. So it wasn't just random split. Still, these samples are very, very similar by size. So with our experimentation on different folds of different sizes, we saw that maybe scores on samples of the same size would be closer to each other than scores from samples from different sizes. Also, we assumed that distribution of classes would be more similar, because even if the split of this green part was not random, anyway, it is more likely that these molecules will have like similar distribution of zeros and ones, right? How many zeros, how many ones in the test, how they bind and not binds, binders of and non-binders. Then we had now training set. Training set was much bigger, and number of binders would be really different. And we didn't know what is how many binders in any part of the test. So,
okay. So
all of this, yeah.
Finally, your conclusion that public and private would be better correlated, it happens to be true, or
it happens to be true.
Okay.
Yeah, it happens to be true. Because I can show you, if I spoiler all the presentation here, this plot I did after deadline. It took a lot of typing, but I did it. I scored different models, a lot of them, like around 30, 35 models, and got private and public scores and just plotted versus each other. And you can see that correlation was quite high between public and private non-shared part.
Okay, I see. Thank you.
And in red, here are the models we selected for our final solution. Almost all good models. We could also select this, but it had a very low public score and high private, maybe just a random luck for this model. Anyway, if we go back. So yeah, for this part, we just decided to use public leaderboard scores for selecting models for ensemble. And don't use this approach. Anyway, one model did use it. Actually, also I can add for this, I said already that we have one model trained in this way with validation on non-shared building blocks in our final solution. But also I did some experiments and got also trained similar model on similar train and validated on shared building blocks. And public scores were really close, very close to each other. So this approach we didn't think will work better than using just public scores. Also, if you wanted to ideally, you want to find a representative validation fault. But for this competition, you actually had to find a lucky fault, which would allow you to get scores close correlating with public or private subsets. It is possible, of course, because it's just a luck, a randomness here. So we could do like a lot of attempts. Maybe we managed to find this lucky fault, but we didn't. We didn't do this. So this third group of molecules from the new library is the most challenging part, because here we don't have not a representative validation fault. We don't have also a training data. We have no one molecule is at least somehow similar to this subset anyway. So the only option we had here is to hope that our models trained to predict for molecules with distinct building blocks will also generalize to this new chemical space and give somehow good predictions for these different molecules from the new library. I guess to find a way to improve these models to like to make them predict better, even only for this group, specifically for this group, we could use, maybe we could find some molecular representation which allow model to catch some patterns in this molecule structure, which allow to generalize, but we didn't. We tried a lot different fingerprints for some models, different ways of SMILES tokenization for transformers, for example. And after this competition, I asked other participants how well they models predicted for this non-triazine new library group. Because I also did scored our models, different models. This is XGB boosting model, convolutional neural network model, and our final solution with ensemble of different models. And we mask all other molecules for all other predictions for other molecules, and leave only predictions for this non-triazine new library part, and submit, and can see scores for this particular group. And it is close to zero, almost the same, no matter what model you try. And few people who answered from another topic here also had the same 0.15 after dot score, and this Ricardo also had the same score for this non-triazine group. And also one guy asked hosts, did they see any submissions with relatively higher score, and they didn't answer. I guess they would if there were any such models. So sorry for this, but this part of the competition was not solved by anybody.
Sorry, Antonina. So you were present at the previous talk by another participant, Vlad Vinogradov. Yes. So I a little bit forget. Maybe you can remind me. So his solution also was not so good at private, or as this new library, new course.
Actually, I don't remember if I asked him. Maybe he didn't score his models, because for this you need at least do some work to get the scores after deadline. The hosts did not release yet true labels for test set, so you can just make after deadline submissions to get some scores. That's quite maybe time consuming, because these data sets are huge and take a lot of time to train model, anyway, etc., etc.
Yeah, I see. So
anyway, I guess if somebody had, why they didn't answer for this? Why? So I just conclude no one had better scores.
and so
Maybe they listen to me and write something after this.
So what do you think in retrospective? Is there any way to kind of have non-trivial scores, or you think it's impossible at all?
With this training data consisting of different molecules, I guess it's not possible. Or we have a much bigger set of building blocks, because as I showed you, we had molecules, all of them consist of a relatively small number of different building blocks. They are kind of similar to each other molecules. We need a wider chemical space for this, I guess. But I don't know.
Okay. Thank you. I see.
Yeah. So after this question, yeah, a few remarks on the ensembling, and I also didn't say about the second thing which made our solution outstanding, I guess. The second thing was we ensembled predictions separately for each protein. Maybe somebody also did this, but I didn't see anybody reported in their solution this kind of ensembling. And I can demonstrate you with this table for ensemble for the shared building blocks part of the test. Why we did so? From the very beginning of this competition, we figured out that some models are better for one proteins, and some models can be better for another proteins. For example, here you can see that boosting model give much higher local score for BRD4 protein than this graph neural network model. But for the HSA protein, it's otherwise. This score for boosting is lower than this score for GNN model. So we decided to ensemble predictions for each protein separately. For our part of solution for molecules with shared building blocks, we just used local scores because we had perfect correlation with leaderboard. So we made a separate sample of 2 million molecules for local test and made local ensemble, and using some automatization, we just ran a lot of experiments with it, and selected selected weights given the best scores for this local ensemble, and then we just selected these models and made a submit for them to check leaderboard scores. Because yeah, I also didn't say that in this competition we did use all the available submissions, all. And you can see that some teams, especially these jumped up prize contenders, used very few submissions. So why we did so many? Because we did scoring for each protein separately. So to score one model, you have to make 3 or 6 submissions for one model. We didn't do 6. We only scored non-shared part because we had this good correlation. But at the beginning, we still had to figure out is it good or not. So we scored a lot, different for each protein. And this ensemble consists of different versions of convolutional neural network models, graph neural network models, boostings. That's all. Three different kinds, and different numbers for each proteins. And here public and private scores if we mask non-shared part. And you can see that CNN models, here we used an ensemble of 4, gave the best scores not only locally but also on leaderboard and in our local ensemble, and got them the highest weight, especially for CEH protein, almost because of almost best for this protein from our models. This network was based on the public notebook with some major changes. Like here you can see the model architecture, how to pronounce it right, and the major changes listed here. I will not go to these very details. If you are interested, you can read in our description more details, and also see this public notebook and ask if you have any questions about this architecture. Sorry. Yeah, and about the second part, solution for molecules with non-shared building blocks. We used the same set of, not same, different set of models, only one XGBoost model and 7 different Chimberta models. Chimberta is from Hugging Face, the small Chimberta. They also have large Chimberta, much larger, much more parameters, but this smaller worked better for us. And so in this solution for molecules with non-shared building blocks, we have smaller number of models, and as you can see, we collected leaderboard scores instead of local scores, and selected models by them. So best scores were selected, and the weights were also selected by leaderboard scores. So we tried different ensembles for this part and just selected by leaderboard. And yeah, and that's all. Also we used ranks. The predictions were ranked before ensembling. So that's all about our solution. If you want to ask anything, would be glad to hear any questions. Or
Thank you very much, Antonina. Colleagues, don't hesitate. If you have any questions, comments, or suggestions, you're welcome. You can ask by voice or write in the chat, up to you. So I have a question meanwhile. Can you show again the architecture for the convolutional neural network? Okay, so what is first, why do you have the 3 columns here? It's
these are different versions. We had four models in our ensemble. Yeah.
Okay.
So there's one variation and another variation, and separately MLP block here, here.
Okay. So just a moment. So what is input here?
Input here is tokenized smiles. Smiles converted to integer vectors.
And how do you tokenize them?
For this model, we did use the same approach. It was in the public notebook. They just made character tokenization. So most common characters, there was, I guess, 36 different tokens in smiles. and just map it to integers. That's all.
Okay, but then the input for different. But so first question. So this input is based only on the molecular, or you include these building blocks also?
No, we did use some information from building blocks only for boosting models, only for some of them actually. All other models are just from molecule smiles and nothing else.
From the full molecular and not the building blocks.
Yeah.
Okay. And
Smile string. Yeah.
But so this tokenization, it outputs vectors of the same length for each molecular, or it can be different lengths of the vector.
Can be different, of course. Yeah, can be different, of course. It is padded with zeros to have the same length. So at the
okay.
At the end, you have like a matrix or array of the equal size padded strings, integer vectors.
You use padding. Okay. So, and the next layer is embedding. Okay.
Yep.
So then you have something like convolution 64 filters. So this 64 filters. What are the sizes of these kernels of filters? So convolution, it's where you, I mean, so convolution takes the point in each neighborhood and aggregates it. So what is the size of this neighborhood?
There were different parameters for different versions. We did use different filter sizes. Mostly for our final models, we did use this 64 filters and different kernel sizes. Yeah.
Okay. And do you have any intuition why this convolutional neural network were working so good? But
yeah, that would be good question, but I don't have answer for this. I even cannot say if this is the best model for shared part or not, because we still don't have labels for test. And to answer this, we have to score each model 9 times to get all 9 group scores, and even these scores wouldn't be mean average precisions, just scores after averaging with zeros, because if we want to know scores for different test groups, we have to submit zeros for other groups. And so we don't know actual scores in private and public test. I hope the hosts will release this true labels table.
well,
and I would be happy to make more research on this.
On Kaggle competitions, at least Kaggle by itself almost never releases the
never.
Yeah, it might be released.
Why?
No, because the kind of you can make later submissions to train yourself, for example. So if someone will release the true labels, and it will be spoiled. So up to now, you can make late submissions and see how it works. I don't know. The host by themselves can release it and put it somewhere, for example, I don't know. But Kaggle, I think, never releases.
They did promise. They did a promise in a few topics.
Okay. So maybe
saying they will release. Yeah.
Okay. Then we should wait. Yeah, but I think they will release somewhere.
I still hope.
Okay. Okay.
Yes, because it's kind of interesting, especially for this non-shared part. Which models were best? I don't know. Still, I wanted to know.
Okay. And another question is about, so you use Humberto. Is it next slide, I think?
Humberto, I didn't put it here. There were different version of Cimberta. They differ by different heads, I guess. Not mine part of the solution. Cannot say a lot of
It's
this.
something like fine-tuning of these models, or you use embeddings and build the models on top of the embeddings, like we have done in Kappa.
No, yeah, we used pre-trained model and like fine-tuned on our data, I guess. It's better to ask Andrei about Cimberta. What I can say is that this model differed by different weights of positive classes and different attention heads and also different samples. And some of them, these two are also Cimbertas, but retrained on 5 folds. Each one just without a sample of data to get more diverse predictions, I guess. And this worked better than models trained just in just in all train.
Okay. There is a question in the chat. So what was your computational setup? GPU, memory? So did you use Kaggle only or you something?
We all had different resources. Me personally, I personally have RTX 3090, right? 3090 and 124 GB RAM, and it was enough to train my boostings with 50 millions of samples. Also, I didn't say that each model was trained separately for each protein, but all other models were trained for all 3 proteins at one time. But this is much faster with boostings because one run took in my PC around half an hour. So it was like 1 hour and a half for 3 proteins to train one model.
Okay, I see. Do you plan to write a paper on this? I think you should.
No, not. I didn't. We didn't use anything really special for a paper. I would consider writing paper if I would do some more research on the best model for each group of the test. Each I mean these two, because it is clear with this group no one model predicted a good had good scores for it, but yeah. So if I would have labels for test molecules, I would do more research and I would try to figure out what approach was really the best one for this subset with different building blocks.
Okay. So there is another question in the chat. So you mentioned now about XGBoost about 50 millions. And so the question is, that means you do not use the full data, because full data was something like
yes,
90 million.
Didn't.
Okay.
We didn't, especially for I can say about this. I figured out that boostings model, how to say, got almost maximal, close to maximal scores very fast. If we train our model with 500,000, 3 millions, 10 millions, 50 millions. The best score would be for 50 millions, but almost the same as was with 10 millions. The most, like, it's like achieve some flat point with increasing sample size. So I just consider this. It's not. It doesn't make sense to use additional resources to train on all data and get almost the same, like maybe 6 to 3 or 6 to 5. Don't make sense.
Okay.
The biggest difference was between, I guess, between 500,000 and 10 million in this diapason of samples. After this, the scores increased very low amount, by very low amount. But Chimberto models and all, I guess, all other models were trained with almost all data without our test subset.
Okay. So there is a comment that bronze medal was achievable by Cambert. Plus report got from 20 million to some million increase. So for Camberto, when you increase from 20 to 100 million, you increase the score by 2 or 3 points, and it was enough to get a bronze medal. There is a comment in the chat.
Yeah, this change of scores with increasing sample size was completely different for different models. We also saw that for Chimberto it's very different than with boosting models.
Okay. Colleagues, any other questions, comments, suggestions? Congratulations.
I guess a lot of people finished up with random some medal in this competition.
Yeah. But have you looked in some papers? What papers are telling the same, that it's impossible to predict on this other, I mean, non-shared core or something?
I don't know, because this competition provided the biggest for today set of training data.
Okay.
No one have more data or even comparable amount of data.
But
this is the first one.
Okay, but any maybe not comparable but small data sets, is there something like publicly available in the similar kind of format, or I mean similar spirit? Maybe not the details, but
if we would search papers with models predicting something about anything, we would find good models which work good on a specific subset. But if we try in different settings these models, it's highly likely you don't get the same performance. So
yeah, sure.
I guess almost all published articles present good models predicting with high precision.
Yeah, but yeah, in reality they fail in some. Yeah, that's I agree.
Even for this competition, if we try this CNN model, the best one for shared building blocks, in another small competition with which is ongoing now with different set of molecules, CNN do not work at all. Very low performance. I have no explanation for this. Very different molecules, maybe.
What is the other competition? It's not on the Kaggle platform?
Not Kaggle, yeah.
Okay.
It was in our bioinformatic chat competition group. Someone posted link to exchange.
Okay.
So I guess no more questions. Thank you very much for listening us our solution.
Yes, thank you very
hope
much. So
this.
congratulations with your gold medal. It's a great solution, and you were stable in the gold zone, so that's great. So, and wish you success and new gold medals, new successes, and so on. And
I hope to break this rule because I always finish in this certain place. Three competition
yeah,
I
unbelievable.
participated in always certain place.
Unbelievable.
Yeah.
Yes. Okay, so have a good evening. Thank you very much again. And the video record will be available soon on our YouTube channel. So good evening, everybody. And thanks again.